Okay, so this lecture I want to talk about a algorithm for estimating the parameters associated with a mixture model. So remember, a mixture model has these component densities or component distributions, and they may have parameters associated with them. And they also have the mixture proportions. So that's another parameter we might want to estimate for a mixture model. And so these are, in general, a mixture model could have quite a lot of parameters, and in general, the maximum likelihood estimates don't have a closed form, but there are some very convenient and intuitive algorithms for estimating those parameters, at least initially by maximum likelihood. So the maximum likelihood estimates don't have a closed form, but there are algorithms that we can find to use to at least attempt to numerically optimize the likelihood. So one of those algorithms, and the one we're going to talk about today, is the EM algorithm. It's called the EM algorithm. It's very famous. So before we talk about it, let's have this is a Wikipedia article on the EM algorithm. So I'm just going to take you there a minute and show you this picture here. So this picture here on the right-hand side represents the way that an EM algorithm, or kind of shows an animation of how the EM algorithm is fitting a mixture of, in this case, two multivariate or bivariate normal components to a data set. So the data set are just the points in the scatter plot are assumed to be, those are the x's, and each point is an x, and it's assumed to come from a mixture of two normal distributions, where each normal distribution has some mean and some variance covariance matrix. So the parameters we might want to estimate here is the relative size of those two mixture components. That it is the mixed proportions. We want to estimate those. That is, what proportion of the points are from the red and what proportion are from the yellow, and then the mean of each and the variance covariance matrix of each. So the colors here are not observed, they're inferred and actually just kind of thresholded when they plot this. So they're just added for visual representation. So if you remember in the last lecture, we talked about the latent variables, the component memberships, the z's, these z latent variables. So think of the colors as kind of representing the z's, but remember there's some kind of distribution on the z's. So actually they've kind of thresholded each one to assign, show the color that has the highest probability for each point. But so in fact, there could be some uncertainty about which component some of these observations should be assigned to. And in the algorithm itself, as we'll see, there's actually that uncertainty is accounted for. So the color, they seem to have just colored it red or yellow, but there ought to, in some sense, be some kind of weight associated with each point here. So the way the algorithm is working is essentially iterative. So each iteration, it's kind of iterating between estimating the mean and the variance for each component and the proportion, and then estimating the component memberships, the z's. So the way to think about this is, this iterative thing is, if you knew where the means were, if you were given this solution here, for example, and told where the means were and the variance covariance matrices were and what the mixture proportions were, then you could use the methods we've looked at, the simple Bayesian computations, to compute what's the probability for each point that it came from each of the two components. So that's a simple Bayesian computation. It's the two-class problem that we've already looked at extensively. So think of that as estimating the z's. Really, it's computing a posterior distribution or a conditional distribution on the z's, given the means and the variances and the mixture proportions. Right? So that's one step. So given the current estimates for the means, variances, and mixture proportions, that is I'll call those the parameters. Given the current estimate for the parameters of the mixture, we can estimate the conditional distribution of the z's. And then the intuition is that if we knew which component each observation came from, we could easily estimate both the relative proportion of the two components and their mean and the variance. For example, if we know which observations come from the yellow cluster, then we can just use the sample mean of those observations and their sample variance covariance matrix as the maximum likelihood estimates of that normal distribution. Of course, we don't know what they are, and so we have to do something that based on our current estimate of the z's. And the idea is that you end up with a weighted estimate of the means and the variance. So when estimating the yellow mean, you weight each point by the probability it comes from the yellow cluster. When estimating the red mean, you weight each point by the probability it comes from the red cluster. So essentially, and then you iterate between those two steps, estimating which cluster each observation came from and the means given those kind of fuzzy allocations. Okay, so that's the kind of the flavor of the EM algorithm. So to write down the EM algorithm more formally, we need some notation. So here's the basic idea. The reason it's called the EM algorithm, it has these two steps that they call the E step and the M step. But so in this notation here, theta is the parameter vector that we're trying to estimate, and theta 0 denotes the current value of that parameter. So we've got a current value for theta. Let's call it theta 0. And so that this first step defines what we call the Q function, which is the expected complete data log likelihood. So look at this P of D given Z, sorry, P of joint distribution of D and Z given theta. We called that the complete data D and Z before. So this is this is a complete data log likelihood here. So it's, imagine that if you knew D and Z, this is the log likelihood you would compute. Of course, we don't know Z, but just hold that thought for a moment. So this is the log likelihood we would have if we observed D and Z. Okay. So we don't observe D and Z. So what are we going to do about Z? We don't observe Z specifically. So what are we going to do about Z? Well, we take the expectation of this log likelihood with respect to the distribution, the conditional distribution of Z given D and our current guess for the parameter, because you know this distribution depends on the mixture parameters, so we need to have some kind of current guess in order to compute some essentially guess for Z. So this is a conditional distribution on Z. Think of this as estimating, quotes estimating, which component each observation came from, or at least the relative probability it came from each of the components. And then we take the expectation of this complete data log likelihood with respect to Z. And we call that function Q. So Q is a function of theta because it arrives here, and it also depends on the current value of theta, calling theta to 0 because that comes in here. Okay, so theta 0 is the current value of theta, and then we compute this Q, which is a function of theta, given that current value of theta 0. And so that's called the E step because it's taking the expectation of the complete data log likelihood. And then the second step of the EM algorithm is called the M step. We just find the theta to maximize Q of theta 0. Or here I've replaced theta 0 with theta I. Theta I represents theta at the ith iteration. And the idea is that this tells you what the next iteration of theta will be. So theta I plus 1 becomes theta 0 in this expression. Okay, so that's the EM algorithm is just to simply repeat those steps. And what the EM algorithm guarantees is that every iteration of this algorithm will increase the log likelihood. Not the complete data log likelihood, but the log likelihood, which is what we want to maximize. The log likelihood is P of D given theta. Okay. So every iteration of this is guaranteed to increase P of D given theta for reasons we may look at later. But for now, let's just have a look at these two steps, and let's just think about what these steps look like if we just want to estimate the mixture proportions. Let's suppose the two distributions are known. Okay, so we've got x1 up to xn. We'll just do a mixture of two components. So we're going to assume that they come from f of x, which equals xx, iid. I'm just going to do a mixture of two, so I can just write it out. Pi1 f1 of x plus pi2 f2 of x. Okay. So I wrote it wrongly last time, but we can write down the complete data likelihood as the product over J and the product over K of, okay, sorry about the, I usually use pi for the mixture proportions, but these are products here. And then this is a pi. So we need a pi K F K X J. I'm sorry, I think I use I in the notes and J in the videos. Hopefully you'll cope with that. Z J K. Remember that Z J K is 1 if XJ came from component K and 0 otherwise. So these are the binary indicators. So this is the complete data log likelihood. We take a log. So the nice thing about this is that it's linear in the Z's. And that's actually what makes the EM algorithm work, or at least what makes it easy to implement, is when this complete data log likelihood ends up being linear in the latent variables, whatever those are. So the EM algorithm is actually a more general idea than just mixture models. We're just applying it to mixture models. We applied to many models where you introduce these latent variables in a similar way. But what really makes it easy is settings where the complete data log likelihood is linear in those latent variables, because then you can take the expectation. So here so let's call it Q. It's going to pi is what I'm thinking about estimating here. So it's Z given X and pi 0 of the log of P of X and Z. I guess I make it explicit that it depends on pi, and I'm thinking of F1 and F2 as given here. So if we take the expectation here, we're taking sum over J, of course, sum over K, E of Z given X and pi 0. Maybe I should use a superscript 0 to avoid. So pi superscript 0 is the pair pi1, pi2 that's the current value of that pair pi1 and pi2. Okay, so the rest doesn't depend on pi. So because I'm assuming that F is known, Fk are known. So I'm just going to take those out and call that bit a constant. Okay, so that's not going to come into the M step, so it doesn't matter. So look, let's just look at this expectation term. Remember, the Z's are indicators. Okay, so the expectation of an indicator is just the probability that it's 1. So what we actually get here is that we get the sum over J and K. This is the probability that ZJK equals 1, given X and the current estimate of pi 0, log pi K, and I'll ignore the constant. Okay, so that's our Q function here. And I guess K here is just summing over 2. If I call this WJK here, yeah, I'm going to call that WJK for the moment. And so actually we get, and of course we want to maximize this subject. So of course WJK depends on pi 0, but I've left that out just to simplify the notation. So if we want to maximize over pi, subject to, well, pi 1 plus pi 2 has to be 1, and pi 1 and pi 2 are obviously non-negative. So if you look at this, it looks just like a binomial optimization problem. And in fact, if you just use the usual way of finding the MLEs for a binomial, you find that pi 1 hat is equal to the sum over j wj 1 over the sum over k, sum over j wjk. Right. So, and pi 2 has 1 minus that. They have to sum. So that's the M step. This was the E step, of course. Okay, so let's just have a look at what this is telling us. If you look at this result here, sorry. Oh, actually this bottom turns out to be n because every point is either in component 1 or component 2. So this is just n actually. So what you're doing here is averaging these W's. Actually, the W's have a name, or sometimes anyway, they're called the responsibilities. These are sometimes called the responsibilities. So the reason they're called that is it's like how responsible is component K for observation J. If WJK equals 1, it's like we know component K gave rise to observation J, so it's completely responsible. But if WJK, let's say, is a half for each of the 2 components, then each of the components is kind of 50% responsible, because really it's about uncertainty in its responsibility. But okay, so the intuition here behind this algorithm, if you look at it, is essentially to estimate the mixture proportion pi 1 here by the estimate of how many observations came from pi 1 from the first component, which is so WJ1 is a weight saying how likely or how probable it is that observation J came from component 1. And we just add those up and divide by n. We average them to get an estimate for pi. And the problem we have is that the W's depend on pi, so we have to iterate that procedure. So it's a very intuitive procedure in this particular case. Again, it iterates between given the current estimate of pi, estimating what the probability is that each observation came from each component, that's the W's, computing the W's, and then estimating pi by the average of the W's. So it's a very intuitive algorithm, which is part of what, part of its appeal is it's very intuitive, very simple as well. And you can extend this idea to estimate not only the mixture proportions, but also the components, the parameters of the mixture. So in the Wikipedia example, the mean and the variances of those normal distributions as well. So we haven't said why this works yet, but this just illustrates what the EM algorithm is in a simple case.